When we talk about CPM, that's computational pipeline monitoring, it can mean a lot of different things for different pipelines, but generally what it's going to be is some kind of field level measurement that's being taken, whether it's flow measurements, pressure measurements, temperature measurements, and those are being put into a database somewhere. So with CPM, what we're doing is we're taking those measurements out of the database, we're performing some kind of calculations on it. The most simple calculation that you can perform is the flow rate into the pipeline minus the flow rate out of the pipeline, and you get some sort of net deficit there or net balance. But there's other kinds of computational pipeline modeling calculations that can be done there as well. You can do temperature correction, you can do pressure correction, you can do time-based correction. If you've got a very long pipeline and you have a change in flow rate at the inlet, you might not expect the outlet to respond immediately. It might take time for that flow rate to propagate its way through. So when we talk about CPM, what we really mean is any kind of calculations or analytics or assessment that's being done to that raw data to turn it into a leak detection prediction. Pipewise can be visualized as multiple levels of leak detection analytics that are working together to provide an overall expert recommendation to the operator about the leak status of the pipeline. So at the very foundation, the ground level truth, that's going to be the measurements that are taken from the field. That's the raw volume balance. And this is what we see most people implementing and then kind of calling it a day. So they say, what's the general line balance of the system? But taking that a step further, just beyond what the actual data is telling us, we have a variety of statistical tools that we'll use to try to understand if the evidence that we're collecting from the pipeline is really indicating a leak, or if it could be indicating any number of other things, transient fluctuations, and so on. So what we'd use typically is going to be SPRT, which is a sequential probability ratio test. This discretizes the data that we collect from the pipeline and breaks it into small chunks of typically 1 minute at a time, but of course all of these parameters can be tuned for your pipeline. So we look at these small chunks and we take each one individually and we say, what does the evidence from the pipeline suggest about this minute of flow? And we'll add that into our hypothesis that there might be a leak or that there might not be a leak. And then we take the next minute and we say, what does this minute say? And we start to accumulate our evidence, and eventually, statistically, the evidence becomes so overwhelming, so confident for us that there must be a leak, that would be when we would move on to the next stage. And that's where we would alarm for our operators so that they could respond to it. Because at that point, we're very sure that the evidence from the pipeline is saying, this is a real problem. This is something you need to deal with. It's not just a false alarm. It's not just a sudden pressure spike or something in the pipeline, but this is a real scenario. But there is another layer on top of that as well. Two other layers. The first other layer that I would talk about is going to be our transients detection. And this is where we try to understand not just the raw signals that we're getting from the pipeline, but we're trying to take a more holistic view of what else is happening in the pipeline at the same time. All of these things like pump starts, pump stops, valve closures, all of these things, even mechanical noise from things like excavation operations or construction operations. All of these things leave transient signatures in the pipeline. And when we can pick up on that, then we can filter the data that's being assessed in the second layer. And we can take out the components of that signal that we think are associated with those transient events. And the result is that it becomes a much more robust system, which is able to deal with those kinds of short-term fluctuations. So instead of instantly accumulating the evidence for our SPRT score, we might be able to pause that or understand how much to weight that data or how to weight that evidence in conjunction with the transients that we're detecting on the pipeline at the same time. And the tool that we generally use for that is going to be a modified form of the earth mover's distance or Kantorovich distance, which is kind of a statistical measure that looks at the individual measurements being taken on the pipeline and tries to understand when the underlying distribution of measurements that we're taking from each of those meters suddenly shifts to a different distribution. So let's say in a very simple example, you've got a simple pipeline and all of a sudden you increase the pump flow rate on it. So your flow rate increases dramatically. Well, your flow meter, which is maybe at the inlet or at the outlet of that line, all of a sudden the distribution of measurements that it's taking is going to shift. So it's going from one flow measurement and you've got a normal distribution of measurements taken around that point. All of a sudden it's shifting to another one. So our transients detection will try to understand has that underlying probability distribution from each transmitter on the system changed? Because if it has changed, that's not necessarily indicative of a leak. It just means that the underlying flow has changed. So being able to tease apart and pick apart those signals is a huge part of how we filter and condition that data so that we know that we're looking at real signals that could be associated with leaks when it comes to our statistical model. And there's one last layer of tech that I would probably talk about, and this is what's really exciting about, I think, the future of where leak detection is going to be the integration of machine learning on top of all this. We're doing our best with statistical measures, with transients detection, with the core ground level truth that we collect from the transmitters on the pipeline. And we're doing our best to be able to make accurate predictions based on that. But what we're really excited about going into the future is being able to incorporate some level of machine learning here, where not only are we using these well understood statistical measures, but now we have an expert system, an expert machine learning system, which is monitoring all of these outputs from these lower levels of our models that are running on the system. And it's going to be providing early warning detection. It can pick up on those leading indicators of leaks. It can tell us before the statistical model even knows. A machine learning model that's well calibrated would be able to say, I think there might be a problem here. And that lets us respond extremely quickly. It lets us change the way that we're approaching our statistical detection. If we already have that prediction from our machine learning model that there could be a problem on this pipeline. And as a result, we're able to get our detection times significantly down. We're talking from a core volume balance perspective. It might take hours to alarm on an imbalance because you might be waiting for the cumulative difference in the flow to reach a certain threshold is typically the easiest way to program that. With the combination of these different features, from our statistical models to our probabilistic transients detection models to our machine learning models, we get that down to minutes. We might be finding your 0.6% leak in 5 minutes or 10 minutes compared to hours that it would take for a typical volume balance. And that's really where the value of leak detection comes in, is having an accurate prediction that you can trust and having it quickly, because the sooner you can respond to that, the sooner you can address it and avoid product release, which is incredibly costly, both from an environmental perspective, a product release perspective, an optics perspective. We want to help you understand, recognize, and deal with that as soon as possible.